So we're going to finish up our notes here on probability by talking about what are called tree diagrams. Now, we're not looking at probabilities of anything that we couldn't already compute using what we've talked about before, but if you're going to compute a bunch of them in a certain situation, a tree diagram is a really nice way to organize all possible outcomes, which allows you, through the rules that we've talked about, to very quickly use the branches of the tree to find the probabilities that you need. Okay? So one example, what if you were to toss a coin twice? What's the probability of getting two heads? Well, if I didn't use a tree, this one's small enough, we could list the sample space, right? If you toss a coin twice, you could get head, 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 tail, tail, head, tail, tail. That's the four possibilities. The probability of getting two heads would be 1 out of 4. There's only one way to do it out of the 4 possibilities. So we don't need a tree technically to do it, but we could organize it with a tree. Okay? If we're tossing, anytime you're doing something repeatedly or you have these multiple events that are coming along one after another, a tree is a really nice way to organize it. So what you do is you list, for the first thing that would happen, all the possible outcomes coming out of these branches here. So if I toss a coin, there's 2 possible outcomes. So we call them branches. I have 2 branches, and I label the outcomes. Here I put an H and a T for head and tail. And then you write the probability that that occurs, which would be 1/2 for both of these. And then you think about what's going to happen next. We're going to toss the coin again. So out of each of these, you're going to get head, tail, head, tail. There's 2 branches coming out of each one. So these things are going to grow, we'd say, exponentially fast. As the branches come out of branches, trees can get very big very quickly. But it does give you a way to organize all the information. Tossing the coin's independent, so all of those probabilities are 1/2. And what you can do with the tree then, once you have it, you can follow the branches. The probability of head, head, I would just follow the branches head, head, and then multiply them. The probability this happens and this happens, I would multiply the 2 numbers together to get the 1/4. Here's another example of internet use, and this is pretty old data. This example I got it from it's probably almost 100%, although it was already 93%. I bet all the numbers would be much higher if we redid this survey today, but the Pew Internet and American Life Project finds that 93% of teenagers aged 12 to 17 use the internet, and that 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So you can see the picture is already made there, but let's think about how was this tree made. So you're asking 2 questions. Do you go online? Do you use the internet? The possible outcomes are yes or no. We're given the probabilities. 93% said yes, which means 7% said no, because it has to add to 100%. Then you ask, have you posted a social profile? Yes or no would be the possible outcomes. For those who are online, 55% said yes, so the other 45% said no. If you want to complete the tree, those who were not online could not have posted a social profile, so 100% said no and 0% said yes. So we have the 0 and the 1. And so the question said, what percent of teens are online and posted? So yes, yes to the answers there. So you'd multiply the 0.93 times 0.55, follow those 2 branches, and you get about 51%. Okay, now our last example, our big example of using this. We're going to do one ourselves here. So we have a bag with these colored balls, and we're going to pull 2 of them out without replacement. So we've done an example like this before, but you see I'm going to ask these 4 different ones. It's going to be nice to have the tree to refer back to. So a bag contains 4 red balls, 5 blue balls, and 6 white balls. 2 balls are drawn, one after the other, without replacement. Draw a tree representing the experiment, and then find all these different probabilities. So I originally drew the tree on paper and scanned it in, but I finally took the time and fixed it